Okay. All right. So I think we're going to do about 40 problems, 20 in this video and then 20 in the next one. And I think you can treat this one as a test. See how many of the problems you can get. And again, we haven't been consistent with other than just starting up now with Calculus 5 and Lesson Set 6, 7 and 8. This is going to be really 9 and 10, but you might want to just challenge yourself. Now, I've had a lot of experience with students coming into a pre-cal class and, technically finished Algebra 1 and Algebra 2, and I'll give a 40 question review. And maybe a half a dozen of those 40 questions are the unit circle. People tend to do a little better with the unit circle. It's the newer material and they, pay attention and, in 4 days you generally can figure out what the cosine of 5 pi over 6 is, and some of the students can do it in 2 or 3 seconds, and other folks have to still do the drawings and figure it out, but a lot of progress. But what's disappointing is that out of the 40 questions, median is usually under 10. And that's everything from factoring to graphing to, standard Algebra 1 and Algebra 2 questions. So that tells me that a lot of people are memorizing for a test and not getting any long-term memory or conceptual awareness. So I think that comes from doing a lot of problems. I think that's why teachers tend to know what they're looking at, because we keep going over it and over it and over it. And since 1993, I've got a different way of teaching where I go over it exponentially more than in a sequential environment. Okay, so getting lots of looks, and the more looks you get at something, tend to make more gains, conceptual and mechanical. Now, I like to pressure myself with a high volume, and I don't work at 100%. Anybody who's watched the videos can see that. And Yasser certainly can help me out with that. And he can attest to the fact that I might make my fair share of errors. So when I take a 100 test question and I want to do it quickly, I work at about a 95% accuracy. Now, if I want to make sure that I'm handing it like a final exam, a key to a colleague, I'll take my time. I'll check my work and I'll make sure things are right. But to make progress, and I'm not doing that with these videos. I'm not doing these problems out. I wrote all the problems on the board, hoping to make this process a little more amenable to viewing. All right, so I've got problems on the back side, problems on this side. I don't have to shuffle anymore. I can pay more attention to the screen and hopefully help people out a little bit more. But each time you see a problem, and I state a problem, just pause the video, see if you get it right. And then what you want to do is the next time we do this, which maybe it'll be the end of next week, maybe every couple of lesson sets, test often. See if you get more right. Same questions, have you learned? Can you put them in your pocket? And I think if you engage in that activity for a month's time, then certain problems that take you a minute right now might take you 5 seconds a month from now. All right? And hopefully some awareness of what you're working with. But if you're struggling with the calculus, it's usually because of the algebraic and trigonometric foundations. So if you struggle with that, go back to the 50 other lesson sets that go from Algebra 1 to pre-cal with what you need to tackle this level. And it's certainly not it's not putting everything out there, but a decent foundation I think can be had. All right, so let's find the equation line tangent ELT to y equals the tan of 2x x equals pi over 3. And we'll just start with the cheat sheet. The tan of f of x is going to become the secant squared of f of x times f prime of x. Okay? We did the quotient rule in the last lesson set, and we looked at the quotient rule, sine x over cosine x, to develop that mechanically. All right, so where are we? At pi over 3? No, we're really at 2 pi over 3. So here's your unit circle broken up into 3 parts. The first part is a little bit more than 1 radius length, and it takes us up to a 30, 60, 90 triangle, 60-degree angle, and that's the famous root 3 over 2, 1/2 ratio. But we're here because we're doubling that. We're moving twice as far, although I didn't draw that too well, twice as far as pi over 3. And that's going to work into the chain rule. That's going to be the times 2 over here. All right, and so what is the height? Tangent is sine divided by, so height divided by width. Well, the width changes signs. Minus 1/2 root 3 over 2. So the 2's cancel and we get minus root 3. So x minus pi over 3, that's our input, gets us an output of minus root 3. And now we have to find the secant, and the secant is the reciprocal of the cosine, so it's minus 2. And if we do minus 2 squared, we get positive 4. But positive 4 times 2, because we're going to get, the chain rule, it's going to get us an 8-to-1 ratio of change. All right, so this secant squared of 2 pi over 3 was negative 2. Negative 2 squared 4 times 2, the derivative of f prime of x is, not the derivative, f prime of x is 2. So, gets us that. Now let's look at it from a graphical perspective. So the tan of x has a period of pi, and the arctan goes from negative 90 to 90, or minus pi over 2, to pi over 2, and it looks like that. It's a rational function of sorts, sine over cosine. And so if we're doubling and we want to have negative pi over 2, then we're going from minus pi over 4 to pi over 4, which is a change of pi over 2. So the next branch is where we're going to get 2 pi over 3. Okay, and if we looked at, this is 0, right? Negative root 3 is about negative, here's negative 1, negative 1.73, so I'm about there. And if I were to draw the tangent line, right, at this location, I'm going up at 8-to-1, and I hope it looks to be accurate. You can go to Desmos or some graphing function and play with that. All right, so that matches up. Next problem, g of x is the ln of 2x plus 3, and the ln of f of x, very similar. It's 1 over f of x, 1 divided by whatever's inside times the derivative of what's inside. So it doesn't hurt to memorize the ln of f of x. If that's y, then y prime is really the derivative of what's inside over what's inside. Okay, so could you do the ln of x cubed right now? Okay, well, 3x squared. So x cubed becomes 3x squared in the numerator over x cubed in the denominator, and lo and behold, that becomes 3 over x. Well, one of your rules is multiply by 3 there, and the derivative of ln of x is 1 over x, so hopefully that makes some sense. All right, so I will now look at this and go, okay, the derivative of this then is 2 over 2x, parentheses, add x equals, I forgot, add x equals 1. I think that's what was written on the homework that I looked at. Okay, so if I put a 1 in, why don't we do a half? Make life easier for us. 2 times a half is 1. The ln of 1 is 0. So at x minus 1/2, I'm going to get 3. And that would be that. Of course, the 2's cancel. And we get 1 over x. And from the standpoint of rules of logarithms, g of x could have been written as the ln of 2 plus the ln of x plus the ln of plus 3. And the only variable here we have is the ln of x, and the derivative of ln of x is 1 over x. Oh, God, here I am falling down. Got bad legs, you know. All right. And hopefully you at least heard that, and I will pay more attention now to making sure that you can see the problems. So dy dx for x cubed y minus 2x y squared equals 8. All right, now I'm going to try to pressure myself here to write the answer without doing any work. So dy dx is going to equal, I'm going to move 3x squared to the other side. Okay, that's going to have a y prime, so I'm going to let that be the division. And what am I multiplying y by? By 1. And now I think I'm going to get minus 2y squared here will become positive 2y squared. And I'm going to divide by minus 2y, I believe. I think that's my answer. I haven't done it in a long time where I just write the answer on the side. So let's see if I'm right. Let's see if we can get this to be that. All right, we'll do the whole thing out here. So remember, this is really a rectangle. It's got x cubed and it's got y for side lengths. So this is going to change according to the 3x squared dx. All right, the derivative of this, 3x squared, but I'm just going to do the differential, and that gets multiplied times y. Geez, that's in a bad position. Okay, 3x squared dx. Let's get as much of it as I can here. 3x squared dxy. And then I'm going to do this, which is going to be dy times x cubed. Okay, so the derivative of that is, and it's plus in this case, I'm adding up these two layers of change. So I've got dy times 3x squared, times x cubed, okay? Minus, I'm going to do the minus here, minus 2y squared dx, all right, because it's minus 2 dx for this term. And then another minus 2y dy times minus 2x. So I can see I made a mistake already. I forgot to multiply that by this, so this is going to be minus 4y on this side. Okay, so I pressured myself and I came up short. And 8 isn't changing, so that there's no differential there. No change, that's a constant. All right, so what's going to happen here? I'm going to divide by dx because I got to get dy dx. That cancels, and I get 3x squared y on this side, and I forgot to multiply by y. So I can't wait to try this one again another time. So 3x squared y. And then this one is going to be a dy dx, and it's multiplied by x cubed. So I really butchered this, I think. I think I butchered this. Okay, so there's my x cubed here. Okay, so I never came back to that. So I came up short. All right, let's get the correct answer for you. Let's do it out by saying y prime now, because this is confusing to me. All right, so I've got 3x squared y plus x cubed y prime. That's a prime. Minus 2y squared. It's going to have a dx. That's going to cancel. Minus 4xy y prime equals 0. Okay, now I can move things over. So y prime, addition of this becomes subtraction. So you'll see me get better at this as we practice. Multiplication by x cubed becomes division by x cubed. Subtracting 2y squared becomes positive 2y squared on the other side. And multiplying by minus 4xy becomes division by 4xy. And I don't think I came up with anything nearly correct. But it's practice. I haven't done it in a long time. All right, so that was a little shorter way of doing it by saying y prime. It's awkward writing the dx's and the dy's, which is why I think it kind of disappears from view as we do more and more of these problems. All right, ABB, area bounded by. We're going to do it two ways. First quadrant area bounded by y equals 8 and y equals x cubed. So here's y equals x cubed. Here's y equals 8. And we need the coordinates because I'm going to do this in terms of x, and a new way of doing it, I'm going to do it in terms of y. So what I need here is my x values, and that's from 0 to 2. I am going to draw an infinite number of layers, and I have to define a layer, and we've been doing that in the previous lesson set, so you try it. I'm seeing my top function is 8, my bottom function is x cubed. So that gets me the height of one rectangle, and the width is going to be dx, and I'm going to go from 0 to 2. And I like 0, so I can do this out. So 8x minus x to the 4 over 4 from 0 to 2, and that's going to be 16 minus 4, 12. 12 units of area. Now let's do it with, instead of vertical bars, let's go horizontal bars. So the question is, what is that? Well, that's a change in y. So I want to write x as a function of y. Okay, so what is y? Well, if y equals x cubed, then x is equal to the cube root of y. Right. So what is this y value up here? Oh, it's 8. And how far did I go from here to here? I went from 0 over to 2. From 0 to 2. So the cube root of 8 gets me that x value, which is 2. If I was looking at a y value of 1, that's not drawn well, but what's the cube root of 1? Then that distance would be 1 unit. And I can stack those up from what? The y value of 0 to the y value of 8. So I believe if we do it in terms of y, 0 to 8, and we look at the cube root of y, which we want to write as y to the 1/3 dy, well, let's do it out. I like the 0 again, helps me. So I got to add 1, which makes 4/3, and dividing by 4/3 is 3/4. Okay, I just got to drop an 8 in. The cube root of 8 is 2. 2 to the 4th is 16. 16 divided by 4 is 4. And 4 times 3 is, geez, it's the same area. Whether I did the integration in terms of x or if I did it in terms of y. So that was a little something new. But how new is that? Well, if you're starting to understand integration, adding up layers, not a big leap, I don't think. I think with a little practice, we're going to get okay with that. All right. I think when we get to lesson set, I'm guessing it'll be about 60 or 70 because we're only doing a lesson set once every 2 days. So how many videos? I wanted you to get about 40 days of practice. So maybe 80 videos coming your way. Okay. So now, 2 ways. 2 ways. Okay, we just did it 2 ways. So now we're looking at the integral from 1 to 8, 2x dx. And I'm going to ask you to draw it. Now, I don't think if you were in the classroom, I'd want you to draw it. If it was a test, I think I'd want you to get the answer here. Okay, but it's important that you stop and say, can I draw this? Can I figure this out geometrically? And the answer is yes, you can. So you try it. All right, so what does this symbol mean to do? Look at the area under 2x from 1 to 8. Okay, so we got 2x. Let's call that 8 right there. And that's 0. And this is the function 2x. Well, I can see what's 0 to 8. That gets me a height of 16. So it gets me a height of 16. So this is 8. So cut in half, 8 times 8 is 64. So I can see that 8 gets me 64. Oh, I didn't want to go from 0. I said 1. Excuse me. I got a trapezoid now. All right, so I now have a trapezoid. I was just looking at this integration. Okay, so I'm measuring from 1 to 8. Okay, so that's 7 units of width divided by 2 is the trapezoidal rule. Altitude on the left, 1 doubled, it's 2. Altitude on the right, we already did, is 16. So that's 18 divided by 2 is 9 times 7. 63 units of area here. So your integration should come out to 16 units of area. And what do I have here? 1 unit of area that is not showing up. Okay, so I'm really doing the integral from 0 to 8 minus the integral from 0 to 1. That's really what's going on. Okay. So let's do the integration and see if we get an answer to 63. 2x came from what? X squared. I'm doing 1 to 8. Oh yeah, 64 minus 1, 63. Wonderful. All right, I think I haven't moved the board, so I'm thinking that you're actually seeing each problem I'm doing now, I hope. So let's say that velocity with respect to time is given to us as the sine of t. Right? And I like to think about Route 91, here's New Haven, Connecticut, all the way up to Stansted, I think it is called, Stansted, and our friends in, hope they're still our friends, up in Canada. I think it's the little town of Stansted, which is half in the US and half in Canada. But Route 91 is pretty much a straight up and down road, marvelous engineering feat, absolutely straight for our purposes, acts like the y-axis. Right? And so where on the y-axis is Grandma? She's somewhere between 1 and -1 because that's the range of the sine function. And that tells us why we study math, because if she's on Route 91 traveling at 1 mile an hour north or 1 mile an hour south, we got a problem. Because if she doesn't get up to speed, she's a danger on the road. All right, so anybody ever ask you why you study math? Save Grandma. So the sine of pi gets us 3. That's a given. The sine, no, I think I wanted the minus cosine of pi gets us 3. Minus cosine of pi gets us 3. Okay, now why did I write that? Because the position statement we want to find, we want to solve for that, and we also want acceleration. Okay, so how do you get from velocity to position? Integrate. Okay, and if you do that, what did the sine function come from? Negative cosine. Plus c. Okay, if I have sine function like that, or if I move it up higher, the rates are the same here. All right, so the constant doesn't matter. The derivative of the constant is 0. So what's the cosine of pi? The width over here at pi, right there, is -1, and the opposite of -1 is 1. And I want to get 3, then c has to be 2. And the derivative of the sine function is the cosine function. So we now know at what rate Grandma is accelerating. We also know her position on Route 91. And all I can say is get out there and give her a hand. All right. Now, I work at less than 95% when I'm talking to you like this. Oh, Lordy. So now, let's integrate 1 to x, 3 over t dt. Okay, and you can pause the video and try that. Okay, pause the video and try it. Okay, you can look at it and kind of see your answer is 3 ln of x minus 3 ln of 1. And the ln of 1 is 0, so 0 times that's going to disappear. So that's going to be our answer, but we'll get it in a moment by looking at something conceptually. I'm going to give you a true or false statement. Is 2 times the integral of x dx equal to the integral of 2x dx? Now let's see, y equals x. Let's just go over to 3. And this is y equals x, so the height is, let's go to 4. So the height of 4 is 4, and 4 times 4 is 16, cut in half is 8. All right, is it the same thing? So I went from 0 to 4 here. Is it the same thing as this from 0 to 4? Well, 2x is going up twice as fast. So at 4, I really have 8. 8 times 4 is 32. 2 times 4 is 8. Let's see, did I make a mistake over here? So 0 to 4. So 4 units times 4 units is 8 units. Oh, I forgot to multiply it times 2. So that's 16. So this here becomes 16 units. I forgot to multiply by 2. Okay, over here, 4 times 8, 32. But what are we going to do with this? Triangle. We're going to cut it in half. So 16. So are they equal? Yeah. So what do we learn from that? Looks like I can take constants out and move them. So this 3 could have come here, and you're really looking at 1 over t dt from 1 to x. And that is another way of writing the ln function. Right? 1 over t is the derivative of ln of x. And so we're doing technically we're doing 3 ln t from 1 to x and then substituting in. And remember, the ln of 1 is 0. So the second half of the fundamental theorem is going to disappear into the back cave. Okay. So that's out of here. Now we're going to see if you can write 4x squared minus 8x plus 6 as an integral expression. So you give that a go, and I'm going to look at it conceptually too. Okay, we're saving some time by putting those things there. Easy access. Well, I need the derivative, and I need a coordinate. So I picked this because I want you to let x equal 2. Why? Because minus b over 2a, I want you to have x equals 1. Minus b over 2a is going to become something easy to work with. And what is minus b over 2a? It tells me that at 1, I'm at the vertex of this. At minus 4 plus 6, at 2. Not that I definitely need the y value, but I want to concentrate on x equals 1. All right, so how do well, I can show you that 1 gets you a 2. All right, and now I need the derivative of this, which is 8x minus 8. I didn't put enough. Need more room here. 8x minus 8 dx. And from 1 to x, I'll do dummy variables. 8t dt, doesn't matter. Right? So maybe it's better for you if I keep the x. As I say, I'm pretty sure machines handle that now. All right, so let's look at this 8x minus 8. Well, what does it do at 1? Changes signs. Right? This is 8x minus 8. Okay. Well, let's go from 1 over to 2. Let's go from 1 over to 2. 16 minus 8 is 8. Well, that's a right triangle. Right, so how much area has accrued? Well, we don't need to do it fundamental theorem. We can look at the triangle. So from 1 to 2, from x equals 1 to x equals 2, we have a width of 1, a height of 8. Looks like we've changed by 4 units. And 4 plus 2 should get me 6. Well, let's put a 2 in. That's 16 minus 16 plus 6. Oh, by God, we got 6. So that area accumulation is batching. Now, what kind of derivative values do we have here? We have negatives. Well, this is a bigger negative than that one. A little awkward to say. I mean, negative 10 is smaller than negative 8. But magnitude-wise, this has a bigger magnitude, which means I'm going down steeper. Well, I probably can do it right here. Right? The further I am to the left, the steeper I'm going down. I'm going down at minus 10, minus 8, minus 6, so on and so forth, with a multiplier, so those values would change. Okay? But what happens at 0? It's flat. Well, there's your vertex. And then your values, your slope values are increasing. Right? The derivative of that, there's a slope. This slope is actually going up faster, and it's a bigger magnitude. Bigger magnitude as I go. And what else can I say? The first derivative is always increasing. Oh, what kind of shape do I have? Concave up. So I want you to hear these every day. And I'm not going to drill you for a half an hour on that. I'm just going to keep mentioning it daily until you take it in and go, oh, how do I know when a function is concave up? 2 ways. When the first derivative is always increasing, which implies the second derivative is positive. I just want to keep saying it. And I think it usually takes about 4 days, and this would probably be day 3 since we started up with doing this on a consistent basis. Okay, so we just took a little peek at that from the conceptual side of things, a little deeper discussion. Okay, now we're going to do y equals 2x cubed minus 6x squared. No, I don't think I just gave you minus 6x plus 7. Okay, so that's actually a graphing form again. Do I want to do this way? Now let's do it this way. Let's do minus 6x squared minus 10x plus 1. Okay, so what do we know? we know that at 1, I'm going down at 10 to 1. And it's a positive x cubed function. So it's got to look like this. And now I shouldn't have drawn that yet, because it looked like I put that at the point of inflection. Okay, the x value of the point of inflection. So I'm not going to draw that quite yet. So positive 6 divided by 6 at x equals 1. There's my point of inflection at 1. Nice easy number to plug in. Minus 4, minus 14, plus 1. I don't like the number 13. I'm going to change that to 5, because that's going to change all your questions. I'll go back to 1. I was wearing the number 13 when I blew out my knee. All right, so let's go look at this again. Minus 4, minus 14, plus 1, 13. Okay? And I'm going down at 10 to 1. So if I'm going down at 10 to 1, when x is 0, so I'm at 0, 1, so it's got to be down here. 0 gets me 1, that's your y-intercept. And you're going down at 10 to 1 here. Now if you look at some of the completing the cube videos, you'll know that this is a minimum rate. I'm going down faster than 10 to 1 right there. All right, so I already found the y value. The y value is 13. And now, I'm going to do the calculus in a minute, but c minus 3ah squared is going to get me the slope at that instant, so I can write this in graphing form. Right now I have 2x minus 1 cubed minus, I'm going to get a minus x minus 1 plus 13. And so what's c? Minus 10 minus 3, a was 2 and h was 1, and we square that. So I'm going down at 13 to 1. Whoa, no, 16. So I'm going down at 16 to 1. So that's here. Okay? So what's the equation of the line tangent to the cubic? People may not have realized this, but it's that. That is the equation in graphing form. Okay. And why is that happening? Because when you put a 1 in here, there's no value. And remember, we've done some work with cubing, right? We've done a lot of work with cubing that. That's 9 decimal places with a 1. There's no change. This is not changing. All the change is coming from this. Right? Just to show you, 2 gets you what? 8, and 2.001 gets you 8.012, 006, 001, and I think it's real important that you go to the Algebra 1 to Trig videos and learn all about this. Because then it really makes this much more understandable. All right, so now what's our max and min? We're going to find the local max and the local min. That's where slopes are 0. But I'm measuring from 1. 1 plus or minus 16 over 3 times 2 is 6. Those are the answers I'm going to get, plus and minus, for the x values. I'm not going to work with that and plug it back in to find the y values. But if I was looking for the values are y's. If I want the x value at the local max and the x value at the local min, well, that's what I'm looking for. Okay, so now we're going to come up with all those numbers using calculus. All right. And we can tell that the concavity changes at the point of inflection, so minus b over 3a is a quick answer for that. But let's do y prime. Y prime is 6x squared minus 12x minus 10. When is that equal to 0? Minus b over 2a. I like to put this in graphing form. So minus b over 2a is x minus 1 again. That's showing up, right? That's got a 6. That's got a squared. And if I put 0 in, I want to get minus 10. Right now I get 6. So I got to go down 16. Did I do that right? Yeah. And so when is this? I'm losing my train of thought. 12x minus 10. Yeah, we want slopes of 0. So 16 divided by 6. And I get 1 plus or minus the square root of 16 divided by 6. And I believe that's what we had. Yeah, I'm remembering now. But I have a real problem with short-term memory now. Too many knocks to the head. So that gets our x values, right? How do we prove which one is local max, which one is local min? We've got to do, and by the way, that's the vertex, right? That's a minimum. That's a minimum range value. Right? So that was our smallest slope on this. Right? These are positive slopes, 0. Then we go down. We go down fastest right there. Okay. Now, let's get the second derivative for concavity. Double prime 12x minus 12. When does that equal 0? When x equals 1. When x is 0, I've got a negative, so when x is less than 1, this is negative. I should graph it, I guess. 12x minus 12 goes through at 1. So there's my negative values, there's my positive. Negative means concave down, positive second derivative concave up, and that happens at x equals 1. Okay, so a little algebra review. Well, it's not really review, because I don't think putting cubics in graphing form is really out there that much. Should be. It's just completing the cube, same thing you do with completing the square. So hopefully it'll become mainstream. So the limit as x goes to 2 of 3 to the x minus 9 over x minus 2 equals what? Hey, pause the video, you think about it. I wouldn't expect you to be able to do this yet, but we're repeating a conversation here. The conversation is seeing that this is the function 3 to the x, and when I put 2 in, I get 3 to the 2, and when I put in 3 to the, I did this actually, 3 to the 2.001, I got 9.0989, and it kept going. Okay, now what do you, how would you describe the slope here? Well, I see this number could have been 3 to the 2.001, and I would have had 9.0, I forget what it would be, but it would be closer to the actual rate of change of this function at x equals 2. Because what have I written here? I've written 3 to the 2.001, and more zeros, so let's just keep it at the 30 mark. Okay. Well, actually, no, let's go to 3 to the 2.0001, and therefore this is, this is 2.0001, and this is 3 to the 2.0001. Okay, so what are my x values doing? I think they're going to 2. From the right, I'm only doing a one-sided limit here. Okay, but I could have done 1.999 here, and we'd get the same result. All right, so what is y2 minus y1? Y2 minus y1, let's do it generically. Let's say that this x is even closer to 2. That I can do 2.01, and then this would be 3 to the x, and that would even be a better Phillips screwdriver for finding the actual rate, because these 2 points are even closer as x goes to 2. And I think x minus 2 would be my second x, and that would be my first. I think that's x2 minus x1. And I think 3 to the x minus 9 is y2 minus y1. And it came out to be the change, 0.001 looks to be very close to 9.9. Now, what is the derivative of 3 to the x? I made a mistake on the quotient rule, and Yasser caught it, thankfully. Right? I didn't say the ln of the base. So the derivative of 3 to the x is the ln of 3 times 3 to the x. Now, for those of you who are coming into these as kind of just a review process for calculus, you probably did L'Hopital. But if you did L'Hopital, you didn't have this conversation. All right? And these are hopefully trying to get people to see the y2 minus y1, x2 minus x1. It's often a little difficult to see. But that's what's going on. Now, I didn't show all of that, did I? No. I got to get this a little lower. Well, I'm hoping that this process can get a little better each time I keep doing it. All right, so as I say, I put this in the calculator and I got 0.0989, which is approximately 9.9. Now, what is the ln of 3? Approximately 1.1. And what is 3 squared? It's 9. And what's 1.1 times 9? Yeah, I'm getting a real accurate process here. That's an exact answer to this problem. All right. Let's see, I've got, ready for this? Okay, here we go. I'm going to try it. First time. Stuck there. Aha! Look at that. Wow, now I can just keep flying. So what's y prime? Yeah, a week from now you'll write this answer in 5 seconds. Okay? But I think at this stage, what did sine function come from? The negative cosine t function. Integrating. And I'm going from 3x to x squared, which becomes minus cosine of x squared. Minus a minus actually becomes plus cosine of 3x. And that's what y equals. So what's y prime? Got to do the chain rule. Minus cosine becomes the sine of x squared times 2x plus derivative of cosine is sine of 3x times 3. So there's y prime. I wonder if looking at this, I could figure out how I could get that. This is a 2. Gee, it looks like I could just drop x squared in there. Sine of x squared. And what's the derivative of x squared? 2x. I think I can just drop 3x in there. I'll get the sine of 3x times the derivative of 3x times 3. Now we're going to actually play around with this and go somewhere with it in the next few weeks. But that's the mechanics for finding y prime if you got a situation like that. Well, that's a couple of weeks, a couple of days. I don't know. It's a 5-second question. All right, this one really throws. I haven't given you this yet. That really throws people. I'm hoping that kids coming from my class, they see that for the first time, they remember 2 things. One, when you don't know how to do something in math, always try to rewrite it some way where you can rewrite the problem differently. That was a hint for students in my classes. So how do we write that? Well, we've practiced that a lot in those 50 lessons set. X minus 1 times what is x cubed minus 3x plus 5. Well, I need an x here. Here's my x squared. I got to get 3, so I got to take 2 more away. And minus 1 times minus 2 is positive 2. And so I need plus 3 over x minus 1. To check that, I plug 1 in here and see if I get 3 out. 1 plus 5 is 6 minus 3, yes. So I checked it, and it works. And so therefore, another way of writing this is x minus 2 plus 3 over x minus 1 dx. Rate times time gets us amounts. And that's basically where this is headed. All right, so can you tell me what the integral of x is? X squared over 2. Minus 2. Integrate. Minus 2. Minus 2x. Integrate. 3 over x minus 1. Plus 3 ln of x minus 1. Okay, so if you took that derivative, right, you'd have 1 over x minus 1 times the derivative of x minus 1, which is 1, times 3, gets you 3 over x minus 1. Okay, plus c. Because we don't have any parameters here, any limits, goalposts. All right, so the limit as x goes to 0 of x times x minus 5. Well, let's do a little algebra. Let's cancel the x minus 5s, and we get x plus 5 over x. It's basically that function. So as we go to 0, we've got an undefined situation. So it might be helpful to graph. The y-axis is an asymptote at x equals 0. We know it goes to 1, so let's get our x-axis. Let's get our height of 1 there. As I move, so this could have been written as 1 plus 5 over x. Okay, so what happens when I start putting in numbers like 0.01 right there? Yeah, going up to infinity. And what happens when I put negative 0.001? I'm going down to negative infinity. limit doesn't exist. I've got to go to the same value. I've got to see a trend in the table towards something that I can name, whether that be a function or a constant. Got to be able to name what's happening. I can't. All right, so does not exist. All right, so this is a lengthy video. This is test day. So now I've got f prime of x is equal to 5 minus x squared times x plus 3 cubed. And I want to know when little f is increasing. Okay. Well, what's little f? Little f, I have to integrate this. I don't want to integrate it, but I do know it's increasing when slope values are positive. So I want to know when this thing is positive. So I'm going to graph it. At -3, I have a cubic root at -3, and at +5, a quadratic root. And if I put in a big number, squaring always gets me positive. And if I put a big number in here, I get a positive, and a positive times a positive is a positive. So I'm going to get something that looks quadratic, and then something that looks cubic. And I have an x to the 5th function, whose end behavior is correct on the right and correct on the left. Yeah. Okay, I think that's right. So if I put in 6, for instance, -6, what the heck did I write -3 for? Oh, that was this one. That's right, and this was 5. Okay, that's correct. So if I put -4 in, for instance, that's a negative, that's a positive. It's going to be a negative product. And if I put a 6 in, that's a positive, that's a positive, that's a positive. Okay. And if I put a 0 in, it doesn't hurt to put a 0 in. I should get a positive number. 27 times 25. Oh, yeah, I get a big positive number. All right, so we can live with this. So when am I positive? From -3 to 5. Union 5 to infinity. And if you route -3 to infinity, I give you full credit at this stage. All right, that's reading the problem pretty well for the amount of time we've spent. How much time have we spent on this? Well, probably done it in 6 or 7 lesson sets, but maybe just 30 seconds for each trick, each attempt. So 6 times 30, we spent 3 minutes on it. Of necessary conversation. A lot of my stuff is tangent to the necessary, but it's a calculus course and we deal with tangents. All right, so y prime equals 6y, and y of 0 gets us 10. I wonder if you can write the answer yet. I wouldn't expect you to, but the answer to this is going to be y equals, let's see, 10e to the 6x. That's what we're going to get. Okay, what's the derivative of 10e to the 6x? What's y prime? It is itself. Times what? The derivative of 6x, which is 6. And y prime is equal to 6. What's another name for 10e to the 6x? It's y. And that's what we started with. All right, so now how did I get this answer? You've done it maybe twice. Well, y prime is the same thing as dy over dx equals 6y. I'm going to separate the variables. I'm going to bring multiplication by y to the other side. I'm going to leave 6 on this side, multiplied by dx. Now I'm going to do what? Integrate. These are layers. Dividing by y is the same thing as 1 over y. I'll put the constant on the right. So this is the ln of the absolute value of y equals 6x plus c. What does y equal? Plus or minus e to the 6x plus c. I hope you can still see that. Barely. Okay, so let's actually put it down a little bit. All right, 6 raised to the x plus c. I'll play with that over here. 6 e to the 6x plus c. E to the 6x plus c. Sorry, the plus c is up here. E to the, right? E to the whole thing there. All right, and that's the same thing as e to the c times 6x times e to the, God, e to the 6x, getting tired. E to the c is just an initial amount. So when you plug a 0 in here, right, we said 0 gets us 10. Well, e to the 0 is 1, so a has to be 10, and there's your 10 e to the 6x. Okay? Now, I want you to tell me what the equation of the line tangent is to x squared plus y squared equals 25 at -3, +4. Well, okay, the equation of the tangent line is going to have an x plus 3 plus 4, and all I need is the slope. How do I find the slope of this? I either have to solve for y or do it implicitly. We'll do it implicitly, and I won't skip any steps. I got 2x dx plus 2y dy equals 0, using differentials. Now, when I divide by dx, divide by dx, divide by dx, what do I get? 0 on the right, y prime on the left, 2x plus 2y, y prime. So I'm going to isolate y prime. Let's divide everything by 2. Okay, so I've got x plus y prime equals 0. So x goes to the other side as -x. And y is multiplication. That becomes division. So now I have a formula for the slope based on an x and a y. And I have an x and a y. So I get 3/4. And there's the tangent line. Now, what were you looking at from your Algebra 2 class? Probably did more conic sections there. X squared plus y squared equals 25 is centered at 0, 0 with 5 as a radius. So we have a 3, 4, 5 triangle. In this case, -3, +4, 5 triangle. All right, and so the slope here was minus the x value, so that's 3/4. All right, does it look like we might be going up at a 3 to 4 clip? Yeah, I hope so. At the coordinate what? -3, 4, so we say x plus 3 plus 4. That's that tangent line. All right, just a couple more problems, and it's lengthy here, all right, but it's test day. And so hopefully these 20 problems would take you no more than 20 minutes a month from now. All right, so y equals e to the -x, and I'll just do these mechanically now and not talk conceptually. Well, I have to talk conceptually on the last problem. So y prime is equal to low d high minus high d low, low. D high is itself times the derivative of -x, which is -1, minus high, e to the -x times the derivative of low, which is 2 over low, which is squaring 2x, 4x squared. And you leave that alone. And it's just, can you remember the formula and do it well? All right. So y equals the square root of x from 4 to 9. We're going to play with it. First thing we're going to do is estimate with two trapezoids. 4, 9, altitude 2, altitude 3. So the first trapezoid splits that in half, 13 halves. So I'll write this as 8 halves, and I'll write this as 18 halves. Okay? So now, trapezoids. This is shared. So what's the width? The width is 5 halves. We have to cut that in half. So 5/4. Altitude on the left shows up once, and that is 2, or the square root of 4. I'll write it that way. Plus 2 times the square root of 13 halves, because it's going to be shared, times the square root of 9. That's 2 trapezoids. 2 trapezoids, 3 terms. 3 trapezoids, 4 terms. 5 trapezoids, 6 terms. The ones in the middle get doubled. The ones at the end stand alone. Putting things in your head. Whether you think it's there or not, it's there somewhere. Our job is to have it come and see the light of day. All right, now we're going to look at, how about 4 left-hand rectangles. So we've got 4, square root of 4 is 2, square root of 9 is 3, and I want to do 4 left-hand rectangles. So there's 1, there's 2, there's 3, there's 4. So it's going to be an underestimate. Okay, and so what are the widths? Well, 4 to 9 is 5 units, and I have subdivision of 4. So each of these is a width. And so 4 is 16 fourths, plus 5 fourths is 21 fourths, 25 fourths, no, I had 5 26 fourths, 31 fourths. I miscounted, didn't I? Because 5 makes 36 fourths, which is 9. So we're going to go from 4 to 9. So that's correct. All right, and I need this altitude, that altitude, that altitude, and that altitude. This altitude will get me 1. This width times the left-hand altitude gets me area 2, area 3, area 4. 4 rectangles, whose widths are 5 fourths, and whose heights are the square root of 16 over 4, plus the square root of 21 over 4, plus the square root of 26 over 4, plus the square root of 31 over 4, and that's where we stop. 4 rectangles, 4 altitudes. If I was doing the one on the right, I wouldn't use the 2. If I was doing the right-hand rectangles, that would be an overestimate, and I would need the number, the 3 over here, or the square root of 36 over 4 still. Not 31, but square root of 36 over 4. Right? I need to bring that in. And those are Riemann sums. Obviously, the more rectangles, an infinite number, will get us the actual area. So why don't you find the actual area now? All right, I just queued up your brain to hopefully say this. 4 to 9, square root of x dx. And what's the way we write the square root of x? X to the 1/2. 1/2 plus 1 is 3/2. Dividing by 3/2 is 2/3. You've probably done this a couple of times already. Square root of 9, 3, 27, 9, 2, 18. Square root of 4, 2, 8, 16 thirds. So 18 times 3 is 54 thirds. Minus 16 thirds is 38 thirds, I believe. But my brain is getting very tired, so I'm stopping there. So that's half of the first test. How many did you get right? I wouldn't anticipate, I wouldn't worry at all about the number you get right now, because you haven't done these enough. Okay? But if you've gotten a lot right, well, congratulate yourself. You're doing really well. If you can already bang some of those out, given the fact that we've been at this a week. Okay, well, we did 4 lesson sets a long time ago. It's got to be current. Got to stick with it. All right, and that's a long video. I'm sorry, but I got to throw some concept in there, and I just did. So maybe look at these things in stages and pieces. Pieces.